Hello, everybody. Um, what I think we do for this new bit of content is just kind of go through a PowerPoint as we would do in lessons, sort of talk through it and see if that helps with different ideas. I'll put the PowerPoint up so you can look at that, but I'll also put a few other links to things that's there. I thought we'd run this kind of Draw the Store Explorer style, where I'll ask the occasional question and you can pause it, and I'll just kind of pretend you're answering. So, like, what was your favourite bit of the lesson? Mine too, yeah. Anytime you want to pause it, have a little think and do things would be really useful. So we're looking at calculating binding energy of nucleon today. So as a kind of build up towards that, two questions. One is about specific charge. And then when you're working out specific charge, what problems are there in those kind of questions? So the specific charge is the charge of a nucleus, say, divided by the mass of it, so charge per mass. When we're doing these kind of calculations, we've got to be really kind of clever with it because they kind of mix up the ideas between ions, atoms, and nuclei. So the specific charge of an atom is always zero because therefore charge is zero. If I wanted to do just the nucleus, I could do the number of protons. And if I wanted to do an ion, well, it would be, if I'd say gained an electron, lost an electron, just that particular charge I'm looking at. So it's something we need to think about. And it's something that's going to come up quite a lot actually when we move on to the optional unit at a later date, because calculating, or rather measuring, the specific charge was one of the first things we did before we got the mass of a proton or electron, or the actual charge thereon. So what you have here are some mass values for different subatomic particles, and what we're doing is measuring them in atomic mass units unit. Originally, the atomic mass unit was the mass of a proton, but what you can see, the mass of a proton isn't exactly 1 U. We're dealing with quite a lot of significant figures here because actually there's going to be very, very small changes, and what we can sort of have a little look at is you've got your electron, neutron, and proton. But when we look at, say, the hydrogen atom, we've got a little bit of a problem there because the mass of a proton and the mass of an electron doesn't seem to add up to the mass of a hydrogen atom, or a helium atom, or an alpha particle, whatever thing that we're looking at there. And this is something we're going to talk about in terms of binding energy. So first little caveat, first little thing to be aware of is the difference between atomic mass and nuclear mass. If it's your atomic mass, we're considering the electrons. If it's the nuclear mass, then we're ignoring the electrons. Most of the time we don't care about the electrons. The mass is so tiny compared to that of the proton and the neutron. It doesn't make a blind bit of difference, but just be really aware when we're doing any questions that that's something we can look at. So if I get 2 protons and 2 neutrons, and you can kind of imagine a magical atomic set of scales which could measure the mass of these individual things. I could put 2 protons on there, 2 neutrons on there. I could then join them together to make a helium nucleus, and it wouldn't weigh the same. Some of that mass would have gone missing. Now, what we have to do is kind of think back to Einstein's famous equation, the whole equals mc squared situation, because that is where that mass goes. When we put those different components together, some of their mass turns into energy and it's given out. The kind of analogy here, the model of this, is electron transitions, electron energy shells. If we've got an electron going from a high energy shell to a low energy shell, it gives out a gamma ray, it gives out some of its energy. Well, this is exactly what the protons and neutrons are doing. Because they're going into a kind of more stable potential, well, a more stable place in terms of their energy, well, some of the energy is given out, binding energy, and therefore their mass has become less because that's where the energy has come from. So in terms of definitions, our binding energy is the work that has to be done against the strong nuclear force to separate out those individual components again. And we'll come back and talk about this when we start talking about electric fields and things like that, because actually it's the same story, it's exactly the same story actually, but we can talk about things being bound in potential wells. So if I wanted to get a nucleus and split it apart to its component parts, it has to do work. The work I'm doing is the binding energy, or to overcome rather than binding energy. There you go. You can do it the other way around. So if I've got these things to put together, some energy will be given out. So one of the things we care about is this idea of a mass defect. What is the missing mass that's occurred when I put these protons and neutrons and put them together? And if we have the mass defect, E equals mc squared, we can work out the binding energy. Now this is a very kind of write down everything and go through it. It's probably just easy to think about, well, here's the masses of my protons, here's the masses of my neutrons, let's add them together, let's take away the mass of the overall nucleus, that's what's going through. But if we've got a particular nucleus, it's got its atomic number Z, if you can see that, so number of protons times by the mass of a proton, plus the mass of a neutron times by the number of neutrons, so the mass of the nucleus minus the atomic number, take away the mass of the nucleus as a whole thing, which we've got. That's going to be our mass defect. E, change in E, binding energy, so change in mass times by c squared, where c is the speed of light, 3 times 10 to the 8. If the formula helps, amazing, brilliant, great. If you just kind of want to think about what's going on here, that's probably the easier thing to do. So here's a little worked example. Now, I think as a concept, this is relatively easy. Where you will all go wrong is typing numbers into your calculators, because actually it's a lot of significant figures and it is worth practicing. Actually, it's worth going back to kind of old school primary school. Let's write it in nice columns so we don't get things in the wrong place. So going through this, you've got some bismuth, 212. And if I weigh that particular nucleus, that is what it is in atomic mass units. We have to calculate the binding energy in mega electron volts. So what you'll always have in the data sheet is the mass of a proton in atomic mass units, the mass of a neutron in atomic mass units. So bismuth has 83 protons because that's its atomic number, 83 times by the mass of the proton. It's got 212 minus 83, so atomic mass, atomic number, neutrons, and that's the mass of the nucleus. So put numbers into the calculator. That there is my mass defect. So actually, this whole huge nucleus, and bismuth is quite large, we're basically missing 2 protons worth of mass, give or take. If I want to convert this into a binding energy, well, if we wanted to do equals mc squared, we would have to sit there and go, right, well, that's my mass of atomic mass units. So let's look at what one atomic mass unit is in kilograms. When I've got my mass in kilograms, I can times it by the speed of light squared. When I have an energy in joules, then, because that's what that would give me, I can then convert that into mega electron volts. It's a lot of hard work, and because it's a very standard sum, well, actually, we just have this number here. 931.3 is how many mega electron volts you get from one atomic mass unit. So if I've got my mass defect, times it by that, gives me my binding energy, mega electron volts. So hopefully nice and easy and something we can go through. Now, working out the mass defect and therefore the binding energy of the nucleus is useful, it's interesting. What we actually care about more is the binding energy per nucleon. One of the things we're going to talk about in the future is fission and fusion. These nuclear processes that make atomic power stations, nuclear power stations, but also make atomic bombs. Well, if you want to start comparing different nuclei, well, it kind of makes sense to compare what is the binding energy per nucleon. If you're a bigger nucleus, you're obviously going to have more binding energy, but you've also got more nucleons there, more protons, more neutrons. So how does it balance out? So if we took helium, for example, its binding energy is that. There are 4 nucleons, 2 protons, 2 neutrons. So 7.1 mega electron volts is the binding energy per nucleon. I'll move that out of the way so you can see the graph in a second, although I might move this after a while. So the binding energy per nucleon is the average energy to remove one nucleon from a nucleus. Now, we often talk about iron as being the most stable element in the universe, and the reason for that is because if we look at the graph of binding energy per nucleon, iron is the most stable. On average, it takes more energy to remove a nucleon of iron than it does of any other element. Oh, there you go. Now, what you can see here is down this side, if I'm going from a big nucleus like uranium and I'm making a bunch of smaller nucleus, that would be nuclear fission. Well, there's a bit of a difference there in terms of binding energy, and that's what's given out in a nuclear power station. If I go on the other side, and I'm joining some hydrogen together to make helium, that's the nuclear fusion process you get in the sun, the binding energy per nucleon, the difference in that is much, much bigger. So you get a lot more energy out from nuclear fusion than you do from nuclear fission. And this all comes from this idea of binding energy per nucleon, and these questions are often really tight together, so we'll have a look at that. So what you've got, let's get that out of the way. No! Let's get out of the way, right? Is some questions to have a little look at. These are available on the post as well as the PowerPoint. So have a little look at these, go through and answer those. This is what I want to post. The other thing I think is really important is getting some notes written up. And that idea of worked examples, how do we go through and how do we do this and how do we practice this so we're not going to make any silly mistakes with significant figures and the number of nuclei there. We've got lots and lots of these to do, so today is just about making sure we're happy with it, and we'll do a load more practice of it another time. As ever, any questions, don't hesitate to ask.